So today we are going to look at the code of practice, the BD 3701, which is the code of practice by the British Standard. Today we are looking at the disposition of the loads, the HA load and the HB load, and how they are being applied at the notional lanes. Now you can see it from the code, the HB load within one notional lane. All the necessary requirements are on the screen. You can see it on the screen. We could also have a situation whereby the HB load is straddling between two notional lanes. The HB load straddling between two notional lanes. You can see it on the screen. There are two conditions for this. You can see the HB load between two notional lanes. You can also see it in another disposition. So these are what we are going to be doing in this class. We are going to do a practical application of this load application. See you.
Hello friends, today we are going to be working on what we did in the previous video where we talked about the design of the beams uh, using the British standard, the BS 5400 Part 2 1978, and we equally talked about the loadings of the bridge using the British design documents and other documents we are going to talk about. But today we are going to be doing a bit of practical example where we can see how these loads can be applied on the bridge deck. So I want you to stay tuned, subscribe if you like this channel, and encourage us to continue.
All right. All right. We are going to be looking at the design of a 200-meter of length beam. All right. We are going to be looking at the design of the 200-meter uh, bridge. The total length of the bridge is 200 meters. Like we earlier discussed about the various codes, today we are going to be concentrating on the BD 3701 and the BS 500 Part 2 1978, steel, concrete, and composite bridge specification for loads. We're going to look at a classical example, an illustrative example. For instance, we are to do the design of a 200-meter of length bridge. We have the shoulders to be 1.5 meter on both sides. Total number of span to be 10. Total weight of the bridge is 11 meters. We equally have the total numbers of girders to be 5. We are assuming an I-section concrete girder. The deck thickness is about 200 mm. Now let's assume that the deck has cantilevers of 600 measured from the center line of the edge bridge to the end of the deck slab on both sides. All right. Now we want to look at the plan. If we're having it as 20-meter span, let's assume it's simply supported uh, span, 20 meters. We're having 10 of them simply supported. So let's take a look at the plan of the bridge. We have it as this. You can see from the diagram we have it. Total width of the bridge is 11 meters. We have the shoulders 1.5, 1.5. And of course, when we do that, we can easily calculate the carriage wheel width. The carriageway width is 11 minus 3 as it stands, which is 8. 11 minus 3 as it stands is 8 meters carriageway width. Now we know from the code BS 5400 per 2, number of national lanes for 8 meters is 3. Similarly, we have for BD 3701, the number of national lane. For BD 3701, the number of national lane is equal to 3. And if we do that, dividing the carriageway width by the total number of national lane, we are going to be having each national lane to be 2.667 meters. 2.667 meters. Now, if we have that, you can see from the board, we've divided the carriageway width into the respective national lane width. All right. Now, the next thing we are going to do, we are going to go into the loading of this deck. Of course, during the loading, I'm going to do a demonstration of application of the load according to BS 500 part 2. And also, we are going to look at the application of the load according to BD 3701. We are looking at them and we are going to have unloaded it. We are going to go into the drawing of the sections of the bridge, uh, configurations of the bridge section, and we'll continue from there. All right. Now let's go over to the loading of the bridge. All right, I was talking about the knife edge load, but before I go into that, let's just look at this diagram. I want to explain something about this diagram. First of all, we are looking at the bridge deck. I want us to look at it in the context of BD 3701. If we look at it in the context of BD 3701, we are going to look at other things, which include number one, we have seen this curve, like I told you, that here, let's assume, we can assume here to be 200, can be 300 whichever way, whichever the designer way. That is why I said to the designer's judgment, whichever. Now, let's look at the lanes. The lanes have been divided into 3 national lanes, like we see. But according to BD 37, in BD 37, we are going to look at what the code says when the HB load straddles between 2 national lanes. If you look at it critically, you see that the HB load, like what we have on the board, straddles between 2 national lanes. There are 2 conditions attached to this in the BD document, just as it was in the BS 5400 part 2. The first thing you discover is that, according to the BD document, that when you have your HB vehicle at closer at this point, you can see the HB vehicle is at the first lane closer to the shoulders. Of course, if you ask me, I will say, okay, we can leave here to the 200, the 300, whichever you choose is. Now, the next thing we're going to be looking at, to what proportion did it straddles into the second lane, which is lane 2. Now, the code equally told us that we can have 2 scenarios. The first, you can have a case whereby you have this space to be less than 2.5. This space to be less than 2.5 before the next lane. All right. But in some cases, and if this happens, when you have this to be less than 2.5, it could be anything. It could be 300, it could be 500, whichever, depends on what you want to do, and whichever that will give you the most critical design. Of course, it shouldn't be much. Let's assume you are given an offset between the HA and the HB. Let's assume we are giving 300 between the HA and the HB here. So what it means is that if that happens, we are going to be having this extending beyond uh, the first lane. It means that the HA load will be extending, the HA load will be extending beyond the first lane. Okay, it will extend beyond the 2.67 meters that we have as the first national lane on this direction.
Now let's look at it. If we have this less than 2.5, for example, here we're having here to be 300, and yesterday we're having here to be 200, our HA load is extended. Now, the second scenario we are going to have is a situation of this same nature, but then we are having here the distance between here and here to be greater or equal to 2.5 meters. If this becomes greater, if this becomes greater or equal to 2.5 meters, is a different scenario altogether. So now, what happens when this, if we have this lesser than 2.5, of course, like I said, it means that our HA load is going to be extending, to this point, whatever it is. It may be more than 2.67, but it's going to be extending towards this direction. Okay. And what happens on that ground? If it is less than 2.5, what it means is that the load, on this lane, the AUDL on the first lane and the second lane will be displaced. And once they are displaced, they will automatically be replaced by the load on the third lane. Okay, so what I'm invariably saying is, of course, when this HB vehicle straddles between these two lanes, you are going to have the lanes displaced. This one is displaced, this one is displaced, and this one takes precedence. So this one comes, uh, it comes, it takes, the space. It goes more than 2.7. So, but if on the other hand, you have your HA load greater than 2.5, okay, what will be displaced in this place will be just this boundary. The load on these boundaries will be the loads that will be remaining from here down, okay? Let me just indicate it. So when this space becomes greater than 2.5, what it means is that the HB load has been able to displace the uniformly distributed HA load of this proportion, of this proportion, of this proportion. Okay, so the remaining proportion remains the same. That means you are going to have it as this. Let me just do a diagram. You see the load, going like this. Okay, so the load becomes of this shape. That is all we have. So the load becomes of this shape, and the code has its own adjustment factor according to BD 37, lane adjustment factor. The lane adjustment factor under this kind of condition is given as beta. Of course, from the BD 37, beta has different coefficients. We have beta 1, we have beta 2. Now, in this first lane, if we have this space to be greater or equal to 2.5, you will have here to have beta. Is it going to be beta 1 or is it going to be beta 2? It's going to be beta 1 of your HAUDL. HAUDL. So you are going to have beta 1 of your HAUDL for this particular thing. That is on a case whereby you have it as this. Okay, and if you have beta 1 here, the remaining lane is going to be a beta 2. Remaining lane will be beta 2, and it's going to be full HA. Beta 2 HA. Okay. Now the remaining part of this lane, should, like we said, remains what it is. The remaining space here, this HB will not be loaded with HA load, or here will not be loaded with HA load. But at the front of the HB and at the back of the HB, let's assume we're traveling this direction. After a distance of about 25 meters, we are expected to load it. After a distance of about 25 meters behind, we are expected to load it. But let's not go into that, since our span is just 20 meters span, so we're not dealing with a distance more than 20 meters. So we're only concerned about this. So, but what I'm trying to say is, once this HB load has traveled into the second lane, what it does, according to BD 37, it displaces a portion of the load equal to the length of the HB vehicle within that particular lane, which is this portion. Okay, so when it displaces it, what is left is you have a shape of this nature, and which is this. And what the code says, that uniformly distributed load is an HA load, and the lane adjustment factor is beta. And if you check beta from the tables, you discover that beta 1 is alpha 1. Under beta 1, we have alpha 1 and alpha. Alpha 1 is equal to 0.274 BL. Okay, 0.274 BL. All right, so that's what we have as alpha 1. Now, alpha 2, beta 2, under beta 2, we have alpha 2, and alpha 2 is 0. What? That is for a span. This is for a span that is lesser than 20 meters. Okay, take note. For a span that is lesser or equal to 20 meters, then we'll have alpha 2. Alpha 2 is 0.0107. All right. We'll have BL 40 minus L. Okay. Loss 3.65 bracket BL minus 20. So that is all we have for alpha 1 and alpha 2. So, having seen this is what we have for alpha 1 and alpha 2. We can now say we can load this deck using any of these methods. Now, we can equally have a scenario like we said, where it falls into a single nodular lane. Then we will follow appropriately what the code have said concerning that. All right. So we're going to look at other factors. I'd like us to look at other factors. Now, having done this, we have seen how this load is going to be applied. Now, take note, we have the HA, we have the HAUDL. So what it means is that when you apply this load, you are going to be applying your knife edge load along. But remember that your knife edge load is not, it's a line load. And if it's a line load, it's a point load that is going to be acting perpendicular to the longitudinal direction of your bridge deck. So if it's acting perpendicular to the longitudinal direction of your bridge deck, what it means is that you are going to vary it along the span of the bridge to get the critical moment for shear and for moment in your design. So now we've seen all these things. We want to use this bridge. Let's draw it out let's get a cross section of the bridge so that we can see and appreciate what we have done. All right. So I'm going to clean it off so we can look at it carefully. All right. So let's get the adjustment factor. The adjustment factor, we're going to have it as 0.731 as the lane adjustment factor for beta 1. So, but we are going to draw the configuration of the deck, the cross section of the deck. Remember, we have the deck to be, we have 5 girders running longitudinally on the deck, below the deck, I mean. So if we have alpha, let's get the HAUDL. We will now have alpha, beta HAUDL. But in this case, our own scenario, we have a case whereby we are not dealing with a figure greater than 2.5 because our figure is lesser than 2.5. And since our figure is lesser than 2.5, we are not going to follow this loading arrangement. The arrangement that will follow is the arrangement whereby we have the HB vehicle displaces the HAUDL of these two lanes. And if it does that, what takes precedence is the next lane, which will be loaded with beta HA load, not HAUDL. Okay. So now we need to get beta HA load, not HAUDL. So if we get beta HA load, we are going to have beta HA load as this. We see beta HA becomes 0. What? 7315, okay, in brackets, HA UDL plus HA KEL. So that's what we're going to have. Now let's look for HAUDL. We have that HAUDL is equal to, we have 361/20 raised to the power 0.67. If we do that, we are going to be having 33616. So we have so we're going to have 45.1. We'll have 45.1 kilonewton meter per national length. Okay. Why the HA matrix do HAKEL becomes 120 kilonewton per national length. Remember, our national length is 2.67. So if we do that, 2.67, we're going to have it as 2.67, 120, 120 divided by 2.67. Okay, that will give us 4.9 kilonewton per meter. So this is what we have for our national lens our UDLs. So we're having this. So the next thing we're going to do, we're going to draw a section of this deck. Remember, I've not applied the lane factor, but if I apply the lane factor to this will give us, we'll now have it as this. Let's clean up. Let's clean up from this point. We'll look at it so that we're going to have our HAUD here to be 45 over 1, 45.5, 45.1 divided by national wall width of 2.67. If we do that, we'll have it as 2.67. If we do that, we're going to have here to be 16.89 kilonewton per meter square. Okay, so this is what we have per national lane. Why this for our HAUD? Then we'll have the HA knife edge load. The HA knife edge load. The HA knife edge load is 120, like we said before, over 2.67. We'll do that, we got 4.9 kilonewton. Okay. Now, having gotten this figure, this is our HA-KEL. Now, if we apply the lane adjustment factor to this, we have a lane adjustment factor of 0.7315. So we are going to have here to be 16.89 and 0.7315. That will give us 0.295, 16 point 0.7315. Okay, so this will give us 12. This will give us 12.35 kilonewton per meter square. Okay, then the other one we have 44.5. 44.5. If we do 44.5, we are going to have it as 44.9 by 0.7315. We'll do that, we'll still have it as we'll do that. I'm going to have, sorry, I'm going to have 0.7 multiplied by 0.735. I'm going to have it as 32.84 kilonewton. So now we've applied the lane adjustment factor. So we can now draw the cross section of this particular deck, which we've just analyzed. Well, we draw the cross section. Remember, we have 5 longitudinal girders, and we've already gotten all we need to do is just to draw a cross section of it. So let's draw a cross section of it, cross section of the deck. All right, having calculated the load for the HA load and the HP load on the deck. Now we've been able to draw the cross section of the bridge. We have 5 concrete eye girders spaced at 242.45 meters respectively, and we have the cantilever of 0.6 meter on both sides. Now, if you look at the loadings, we have the HA HP load at an eccentricity of uh, centricity of 200 mm from the curbs, and we have the pedestrian life load for the bridge, which is 5 kilonewton per meter square. And you can see we equally have uh, a space of about 300 between the HB and the HA load. We have the HA load as 12.35 kilonewton per square meter HAUDL, and HA knife edge load as 332.84 kilonewton per meter. All these are what we've done. Now, the next stage we are going to be looking at is calculating the we're going to be calculating uh, the sectional properties of the HA loads. The sectional properties of the I gather. Now we are going to calculate that. First of all, we are going to do what are the sectional properties we are going to work on. Number one, we'll get the area of the I section. Number two, we'll have the sectional modulus of the I section and the moment of inertia of the I section. Equally, we are still going to work on the composite section. Remember, the bridge is made up of the composite part, which is the bridge deck of 200 mm, and we are going to work on it, uh, determining the moment of inertia of the composite I section, and from there we can begin to solve other problems. Okay, so let's go over to the determination of the sectional properties of this I section. Picking the penultimate beam, you know that we're going to have the section as this. Let's look at the sections.